Welcome everyone. We're starting the panel for the Benchmarking the Data Center workshop. Our panel, it's called Benchmarking in the Data Center and Beyond. And my name is Verónica Melesse Vergara, and I'm here hosting the panel with Oscar Hernandez. Our panel theme will be on, like I mentioned, benchmarking the data center and beyond, so like more a futuristic look on what needs to change, so that we will focus on current benchmarking processes and how they have evolved in recent years or need to evolve in the near future to both support emerging workloads, but also support increasingly complex data-driven workflows and increasingly cloud-native and heterogeneous architectures. So our moderators are Oscar Hernandez and myself. Oscar Hernandez is originally from Guatemala, and he has a PhD in computer science. He was at Oakridge for 12 years, and he recently joined NVIDIA and Mellanox. Oscar has done a lot of work in programming systems, and his expertise spans from working with OpenACC and OpenMP and communication libraries and frameworks like OpenHMM and UCX. Oscar participating in the exascale computing project and NSF computing projects, doing research on programming models, and has served in different committees, the Office of Science, the NHBC conference, and workshops. And then myself, Verónica Melesse Vergara. I'm originally from Quito, Ecuador, and I have my background is in computational science, but I lead acceptance for the systems at Oakridge Leadership Computing Facility. I'm a group leader in the System Acceptance and User Environment group. And I led the acceptance for Summit, and I'm currently leading acceptance for Frontier. So that's where my interest in benchmarking and systems, large-scale system testing comes from, and why I was interested in the workshop and both the panel that we'll have today. I'm also a member of the SPEC High Performance Group, which we're developing benchmarks for different systems, and I serve in various committees for ACM, SIG HPC, and SC conference. And today we have four panelists from four awesome panelists: James Glaser from Oakridge National Lab, Heye Nam from Lawrence Berkeley National Lab, Prabhat Ram from Microsoft, and Gilad Shainer from NVIDIA. James Glaser from Oakridge National Lab is a computational scientist at the OLCF. His research involved drug discovery and biomaterials made from protein building blocks, and he's currently interested in applying AI to molecular design. Heye Nam is a Lawrence Berkeley National Laboratory, and she's a staff member of the Advanced Technologies Group and specializes in high-performance computing, benchmarking, and performance analysis. Her career spans 3 DOE national labs, and her work it contributed to low energy nuclear physics, computational physics, HPC, and research scientific computer to impact NSA mission-focused advanced simulation and computing projects. Heye has led Advanced Technology Systems Center Excellence efforts and supported multi-physics codes to run effectively on Los Alamos systems, and she has a PhD in computational science from Claremont Graduate University. Heye's interests include emerging technologies for HPC and science ecosystem, the science needs driving those requirements, and the substantial interdisciplinary effort to bring technologies from design to production readiness. Prabhat Ram from Microsoft is a principal AI architect in the Azure HPC team, and in this role, he supports AI workloads for Azure's most demanding and strategic customers. In the past, Prabhat has held production and research roles at Lawrence Berkeley National Lab and led the Big Data Center collaboration across multiple industry and academic partners. Prabhat has published over 150 papers, won the Gordon Bell Prize in 2018, and co-edited a book in high performance parallel I/O. Last but not least, Gilad Shainer at NVIDIA. Gilad serves as Senior Vice President of Networking at NVIDIA, and he also serves as the Chairman of the HPC AI Advisory Council organization and the President of the UCF Consortium. Gilad holds multiple patents in the field of high-speed networking, and he is a recipient of 2 R&D 100 awards, one in 2015 for his contribution to core directed network computing, and one in 2019 for his contribution to UCX. Gilad holds a Master of Science and a Bachelor of Science in Electrical Engineering from the Technion Institute of Technology in Israel. So to get us started, our first question of the panel, first welcome everyone. And the first question is, what are some of the challenges you have encountered or you expect benchmark makers will face when expanding to the cloud?
Hey everyone, good morning, good evening, good afternoon. For me, it's morning, so good morning. I'm excited to be a part of the panel, and this is a really interesting question. It's something, so at NERSC, as we're preparing for the Nurse 10 system, we're certainly thinking a lot about benchmarks right now. Thinking about what the future of technology looks like in 2025, 26, when Nurse 10 will be arriving. And cloud is definitely one of those features that we're looking at, because it's kind of, we're thinking of what do we need from the cloud that we could use to enhance Nurse 10? How do we work with the cloud? And we've been thinking a lot about benchmarking. So there's a ton of challenges that we're facing. But the big one that I think we're wrestling with right now is that there is no longer a simple metric. Right? It's not performance. It's not just time to solution. So I saw in the chat, Jen, you were asking, are we optimizing for time to solution? What else are we optimizing for? And that's one of the biggest challenges now, is that it's not necessarily time to solution that we're optimizing for. We need a new metric. We need not just a new metric. We need new metrics in general to be able to say whether or not a system and software and things of that sort are working optimally for the user. So Andrea was saying, it has to be good for the user, and that's what we're trying to benchmark for. So a simple time to solution where we had a very constrained environment in our facility was great, but now once you have a facility and the cloud, the network, there's just so many other components to it, and the users are saying, I really don't care about just a single time to solution anymore as my metric for success. I really have this giant workload with a whole bunch of different components to it. That's really what I'm optimizing for. Make this seamless. So how do we optimize for seamlessness? So there's a lot of new vocabulary, a lot of new metrics that we need to actually quantify. And that's one of the challenges that I think we're facing because of the cloud.
Right. Should I go next?
Yes, sorry, my unmute button was not working. Yes, please go ahead. Thank you.
All right. I think, those are two very interesting perspectives. Maybe I'll just take a slightly different perspective on what I expect people who need to run benchmarks on the cloud, what are the challenges that they are going to face? And I think one of the very first ones is that just because there are so many flavors of hardware and VMs that are available, say on Azure at this point in time, there's an alphabet zoo of options. So you'll have to figure out which one makes the most sense for you to evaluate. Once you're done with selecting a certain VM, a certain flavor of hardware, then to some extent you'll have to discover, what kind of storage resources are available to you, what storage hierarchy actually makes sense. You're never going to be able to control exactly where you end up on the network, so you'll have to discover or I guess work with the cloud provider to discover the network topology. And then there are a lot of things on the node that you may also need to discover. I think, Jens, you're sort of getting at XGMI and NVLink style challenges. But anyway, so that's one of the things that you'll have to discover. Let's say that you've gone through this phase wherein you figured out which hardware you want to run on, what aspects of the system subsystems are relevant to you. Then there's the question of actually running the benchmark. Now I'll quickly note that you will likely end up running on a public cloud. So we do have dedicated supercomputers at this point in time, but you will end up running on a public cloud. So ensuring that you end up on a quiet system is highly unlikely. So there will be other tenants on the system. There will be other users who will be contending for shared resources. So performance variability is something that, again, you should expect, and that is something that you should try and characterize. So obviously, running your benchmark multiple times would make sense. There are aspects of, if you end up running in a container, there are going to be some number of cores that we hold back on the CPUs. So there will be some background activity that's happening over there. So how much of an impact that has on your benchmark, that remains to be seen. There are similar aspects around storage and networking systems in that those are shared resources in a public cloud. So those are things that you'll have to keep in mind, I guess, as you interpret the results of the benchmarks that you run. Now, I will note that a lot of these things do happen on on-prem HPC systems as well. Verónica, you're referring to an acceptance phase wherein you own the system, you keep the system in in a quiet setting by kicking everyone off. But at the end of the day, if the benchmarks have to have any relevance to what users experience when they run, then there are these things that folks running benchmarks on HPC centers have struggled with forever. How do you actually simulate the environment that the user actually faces at the end of the day? I think the cloud just brings that to the fore. But whatever best practices I feel that the HPC system folks might have proposed, some of those could be brought to bear in the public cloud setting. I'm going to pause there.
Thank you very much. Gilad, would you like to comment?
Yeah, last and not least. Yeah, if I knew that you will read the entire bio, I would probably cut it to like one sentence. Make it easier. There is a lot of things you can say about it. The beginning when I looked on the questions, it seems simple, but actually when you start thinking about it, it's becoming more and more complicated. First, who's the benchmark for? It's like the user using the cloud, or it's the cloud provider. Sometimes there are different metrics. The cloud providers wants to maximize the profit, right? So the less overhead on the compute elements, it's better for him. User may look for the performance of what is running, and time to solution is important, right? It's not the only thing, but time to solution is important, because if it's going to take me to run my workload 10x more time than something else, I don't want to use it. So time to solution has importance. And I thought it's probably the better way from my side is actually to look to the future, kind of not looking the back mirror of what exists today in the cloud or what the cloud provides today, but what's the future is going to include, and actually start looking, creating benchmarks for that part. And sorry that I'm taking a little bit more time here. Apologize. I'm going to reduce the time in the other questions. If we look on what's happened from HPC usage, in the future, everyone will need to use HPC. Not just the traditional HPC, not just scientific computing, but if AI goes everywhere and AI fuses itself into scientific computing, and AI brings more things such as digital twins and other stuff, then every company in the world will need to have access to supercomputing. Every company in the world will need to have access to HPC. And not everyone can afford building their own supercomputer, which means supercomputing will need to become a service. Same as electricity is a service. So when you buy an electric device, you don't need to build your own power plant. Same as computing has become a service with the cloud providers. So if I need to have a single CPU, something simple, I can go to the cloud and run it there. But supercomputing to become a service, that requires new elements. That requires us to deal with new challenges. And I think some of the challenges were mentioned before. The first simple challenge is predictive performance. That's the first challenge. If I'm taking a supercomputing workload is not something that contained within a single node. It's not something that contained within a single CPU. So I can put virtualization and make sure that I have all the isolation and security within the node. Now I need to deal outside of the node. And once you deal outside of the node, you have multiple applications utilizing multiple nodes. Now those applications are utilizing shared resources, such as the networking side of things. And this is where you can go into issues where one application will impact another application performance. And that means that I can get access to I can put my supercomputing workload in the cloud, and sometimes I'm going to get X performance, sometimes it's going to be half of that, sometimes it's going to be 5X worse. And that's not a good thing, right? You want to have a predictive performance in the cloud. You want to bring actually performance isolation into the cloud. So things will evolve, and clouds will become cloud native supercomputing, and our supercomputers will become cloud native supercomputing, and they will deal with new challenges. And therefore benchmarks will need to be developed that actually can measure those kind of things. So low-level benchmarks that we can run on a HPC platform can always run on the cloud. Time to solution can also be run on the cloud, but we need to develop new elements such as measuring predictive performance, measuring how well cloud providers provide or cloud system provide performance isolation, for example, and many other aspects as that. So I'm going to stop here. So there is time for other questions, but this is just the beginning. This is just the beginning.
Thank you. Yeah, definitely. Just to like, I guess as a comment on this too, like both having benchmarks that would fit future use cases or current use cases that are emerging would be useful. I mean, for us, like as Heya had mentioned, for like future systems where we're thinking about like the ecosystem, not just like one monolithic middle system, and how do we account for workloads that are going to come from different like systems that are out there, but also what benchmark we can use to even simulate that behavior, so we can run that before we put users on, but making cloud type resources easily accessible. Like the barrier for entry needs to be like, if I'm gonna use this cloud versus that cloud versus this cloud, that's also something I think important that users will consider before trying to compute.
Yep. And I also want to mention that Gilad just brought also a very good point. In HPC, traditional HPC, having a predictability in the performance, even if we own the machine, having predictability because of the massive, the machines are using capacity, there is a lot of variability a little bit there already. Just using the HPC system, there's a lot of variability in the computer performance from run to run. And that's something that we struggle at the center to keep that basically at bay. And then on the cloud, there's other elements that basically more share resources and other software that's running there. But I think that technologies that can solve these two things together, both in HPC and cloud, eventually will help basically understand this better, address this better, but also the benchmarks to basically run that. It should focus on measuring this variability.
Thank you, Oscar. So our next question, it was sort of related to how traditional HPC benchmarks, but how do you envision those traditional benchmarks evolve to take advantage of the cloud native solutions? I think some of you already touched on this a little bit, saying that we have to come up with new things, but and let me start with Heya so that way we can give everybody a chance to begin.
Sure. So this is my least favorite question. I'm sorry. I find that this question is boring because, traditional HPC benchmarks, you containerize it, you throw it on a cloud, system, and you run it. It's really the complexity is not coming from the traditional HPC benchmarks because a lot of those are getting ready to just move over to cloud in a production space. We're really looking now for new benchmarks and new workloads. So the HPC benchmarks of the past, being focused on traditional modeling and simulation, are now going to start including AI, which has a very different way to benchmark, because the interplay between the accuracy and the performance kind of working against each other sometimes. That coming into play, and then also the large scale data experiment benchmarks that we're taking into account. So it's not that we're worried about traditional HPC benchmarks moving to the cloud. It's trying to couple all of the new workloads on top of that, and then moving and leveraging cloud. And that's where the complexity comes in.
Okay, thank you.
I'd agree completely. I think with, I think the way the question is framed, traditional HPC benchmarks, I feel like that's, a different world. And as long as you can containerize them, yep, off you go. Really, cloud native is coming from a very different direction. So things like Kubernetes and microservices and DevOps and, so on and so forth. So I'm not sure how much bearing that world has on traditional HPC benchmarks per se, but I think as Heya just pointed out, like as the world of supercomputing evolves from just traditional computation modeling to hybrid, say AI and HPC, but then even supporting things like complex workflows. Again, think of what the DOE calls experimental observational data. So if you have a bunch of instruments off to the side who are streaming data, and then based on that data stream, some action has to be taken, some compute has to be launched, data has to be moved automatically across regions, so on and so forth. I think that is likely where some of the cloud data solutions may have a role to play. But with regards to traditional HPC benchmarks, I would say just bring it on. I guess throw whatever you have, right? Containerize them, run it on the cloud, and see what you find.
Thank you, Gilad.
Yeah. By the way, if you don't like the question, you can answer any other question that you want, right? It's like someone controls the questions, you control the answer. We can talk about something else, which is always true. If what I said before is going to happen, and we truly believe it will, that everything become cloud native supercomputing. I mean, the cloud for HPC will become cloud native supercomputing, and then on-premise system that we build will also become cloud native supercomputing, because we will want to support more users and more kind of workload and so forth. So then actually everything becomes the same, and Azure or any other public cloud provider will actually build cloud native supercomputer. And the question is now what is cloud native supercomputer, right? Or what is the right cloud for supercomputing? And in our view, first, the basic element of a cloud native supercomputer should be a combination of bare metal performance and security and isolation between users. That's the basic. If we don't provide bare metal performance, we're going to waste a lot of resources, which it's not really a good thing. Now, cloud essentially can be bare metal, obviously, and on-premise can use containers. The things that will need to be common is first bare metal performance with user security and isolation, and that will enable us also to bring some workload which are based on personal information, for example, that we do want to run on supercomputers. So we need to have security and isolation. The other part that is being evolving is what is being called in-network computing, which is actually computing elements that now exist not just on CPUs, on GPUs, but also exist on other components. For example, data reduction is being moved to the network. It can be done on InfiniBand network, and now it can be done on the next generation NVLink, for example, on proprietary networks as well. So there's other things that have been involved, and then traditional HPC benchmarks can definitely continue to be used. If you look on low-level stuff, measuring flops, not sure how interesting it is beyond of the top 500. Running the workloads by themselves is definitely something that can continue to be used, and that's one of the good things to do. But new benchmarks will need to be created, as we mentioned. So for both on-premise, by the way, and kind of public cloud usage or using public cloud vendors. So the predictive performance is one thing, and performance isolation another thing, and ability to measure computing that we receive not from the CPU or the GPU. That's an interesting thing, right? If you have computing on the net, if you do reductions on the network, how do I measure how well those reductions are being done? I can make it like flops, right? If you do this amount of reduction at that speed, it's easy to count. But that's not the impact on a workload, because the number of flops there will be very small compared to what you get from the compute side of things. But the impact on applications can be 40%. So you need to actually create new elements. So the traditional benchmarks are great, and you can continue to use some of them. But essentially, the more important part, and I agree with what was said here earlier, that's not the interesting part. The interesting part is to create the benchmark that actually will give us a better understanding of all the new things that are being created.
Thank you. Jens?
Yeah, I think this is an interesting question for once, because we have to know where we come from and where we want to go, right? If you want to know that. I do agree with Hai and that we need new benchmarks, definitely, and that we need benchmarks that target AI and machine learning performance. And there are some examples out there which try to achieve these objective comparisons of performance, like MLPerf maybe, and that's one example, which are recent. However, maybe it's also timely to ask this question in the context of one of the luminaries of HPC, Jack Vergara, being awarded the Turing Prize for his achievements in benchmarking and HPC systems and being the supercomputing father. So I think it's quite astonishing that that this 1980, so 40-year benchmark still has relevance today, and this was quite a sign of foresight that BLAS and matrix operations play a deep role in current AI workloads, and basically the backbone of enabling the performance of AI, right? So in that context, I think we need to be aware that future benchmarks should be measuring those core metrics which allow us to have AI progress and breakthroughs 40 years later. And I think that it's hard maybe also to just one-to-one move those benchmarks from the HPC system to the cloud, given that you can run distributed benchmarks on an HPC system, but it gets more challenging if you just put them in the container and then expect to get the same kind of performance out of that. So in that sense, I think we need to not throw away the lessons learned and maybe develop new benchmarks that have predictive power for cloud systems. So if we have new patterns, algorithmic patterns that define our AI or other workloads that run in the cloud, maybe workflows, and we can isolate those, then it may in the future, maybe decades from now, prove pretty insight and full and foresight, with a lot of foresight if we find those patterns today, and maybe they will still live on. So that's my perspective on that question. And to summarize what I said earlier, I think one term, because it wasn't recorded, and one term I didn't use, but that I find important in the context of cloud also is turnaround rather than only time to solution. So this does not necessarily impact the training performance of a model, say, but it is a convenient aspect of AI, of cloud-based computing, that we should also take into account in how it enables workflows.
Thanks.
Yeah,
Jens.
may I jump and just add something to Jens, if possible?
Yes, sure.
Make it interesting, right? So we have kind of discussions between people on the panel. Yeah, it's always true, right? You can take all benchmarks and try to bring them in new platforms as well. You know, we need to remember where we're coming from, but sometimes you need to actually understand how good they could. Let's take a simple example, right? Let's say that I'm benchmarking workflows. Essentially, you create benchmarks because you cannot run the full workflow, right, on the system. But let's say that I'm taking Fluent just for, LSDyna, lamps, just as an example, and I'm running that workflow on a cloud, and I get a number X. Is that my number? Is that how do I measure that benchmark? I can argue that the answer is no. I can argue the answer is no, is because if you actually want to understand what will be the performance of lamps on a cloud, you need to run it 10,000 times. Because if in one case I'm going to get X, and in one case I'm going to get 5X, in another case I'm going to get half X, then you need to actually double that in a predictability of the performance that I'm getting, right? And that's becoming a big factor into it. And then you can argue that actually the predictable performance is actually more important than the performance of the workload itself. Because if you get a 10x variant, maybe actually lab's performance by itself, it's not really important anymore. So taking those traditional workloads or traditional benchmark from the past and saying I'm going to run him as is, and that's going to give me a good take of the cloud, not necessarily. You need to actually understand what you want to measure, and then start to create more new metrics actually to be able to measure that on the cloud.
I mean, even on-prem, like that's one of the concerns, and that's one of the things that we do take into account for runtime variability is heavy concern, because it vary even on like our single system that is sitting at the data center, depending on what other people are using, like there is still shared resources. So we do have certain runtime variability that we need to keep. So in my mind, when we're expanding to cloud too, it becomes like way more challenging because the resources that are shared are even beyond our control. Like we have a center system that is offloading or like streaming data coming from another edge that needs to get to the cloud, that needs to get to Summit. It's all like much more complex, but I think having a way to measure the workflow or like understand the workflow, whatever the workflow may be, abstract in a way that we can understand it better, and maybe create some kind of benchmarks that would capture the important pieces would be definitely valuable for what we do. But in general, it's challenging, I think. Does anybody have other comments for this one?
Yeah, I just have a comment, very quick comment. And it's very clear that in the future, cloud native solutions, content native, will also, it's not going to be cloud native bare metal performance, but it's also going to be new technologies, new resources, like in network computing, for example, those sort of things where we need to offload things to the network. And those sort of things are also tied into basically the traditional way we do a little bit HPC benchmarks, because sometimes the benchmarks itself are not they don't basically they could explore more capabilities that are going to be available for the cloud native, and potentially there could be a little bit of evolution there, or maybe not. It could be addressed through a library that is already being used in the traditional HPC benchmark. So that's another perspective. So basically, not only having the predictability in time is a great thing to keep in mind, but also that we're going to have new capabilities, basically, as more capabilities in a cloud native solution.
Thanks, Oscar. So our next question. How do benchmarks need to change to measure the converged workloads that you've mentioned? I mean, we've all talked about already. Everybody has mentioned we need new benchmarks, but how can we actually measure those converged workloads or new workflows that we were talking about? If we're streaming data from an instrument or we have to push something to cloud, how do you think we could measure these new emerging workloads?
So maybe, let me split the question into two pieces, the converged workloads part and then the streaming sort of, workflow. So I guess on the converged AI HPC workloads, I'm going to assume that, we continue to do applied math, I guess, on our CPU of sorts. And then there is the AI piece perhaps running on a GPU or some accelerator. So there are certainly, some basic questions we have to get right first, right? So what is the degree of coupling between the simulation code and the AI inference code? Where is the inference running to begin with, right? Is it on the same node or a different node? What is the interface between the simulation code and the inference code? So again, just to give a quick example, in all of the xScale computing project, like we gave up on IO, saying we can't store the data to the disk. So we came up with all of these interfaces for in situ visualization, in situ analytics. So similarly, I guess there'll be some notion of an interface coupling the simulation code to the AI inference. So anyway, so we need to sort of sort that out, think about bit precision, so on and so forth. And then, yeah, I mean, you can start thinking about, what are the metrics, I guess, associated with this converged workload that now would be relevant. So certainly, time to solution makes sense. I would postulate that to the extent that we may not understand the convergence of these coupled workflows, ensuring that the coupled workflow is actually converging to the right degree of accuracy, that becomes an additional consideration beyond the standard performance metrics. The second part, around the streaming use cases. Now that I think is an interesting one, and I would say that we talked about all of the challenges regarding performance variability in the context of a clean, quiet, isolated on-prem system, and then that fact was, that was going to be a little bit harder to do maybe in the public cloud. This story becomes even more complicated when you're now talking about streaming from an edge device over a network that you may not control or provision completely down to, say the cloud or an on-prem system. So I think I would say that, there are at least three aspects, we should keep in mind. There's performance, there is productivity, there's cost. So on the performance side, I think new aspects really come in around, of course, how fast you're able to move the data, what the latency there might be. I think one will have to pay attention to the storage resources that are now available, say in the cloud. So to the extent that there is a storage hierarchy involving hydrating systems that are closer to the compute elements, you'll have to take that cost into account. On the productivity side, I think I do want to note that dynamic provisioning and elasticity are unique aspects that the cloud provides, which is again something that historically the on-prem HPC centers have struggled with. So I think one would need to account for how easy is it, based on an event, based on an experiment that's conducted, how easy is it to provision resources, both networking and compute on the cloud. So that's something that you can keep in mind. I think a lot of our discussions with customers around cost, I think there is an aspect of the cost of ingress and egress of exactly this data flow. So I would think that any meaningful benchmark should probably take into account that cost as well, beyond just the cost of storing the data and doing the actual compute.
Thank you, Gilad.
I'm the second now. It's better to be the last, not the second. I think we probably covered some of the things already here, but I agree. You can divide this question into 2, 3, 4, even more. The last part, I still debating. It's not sure that we have a good answer for that. Meaning, as we moving towards cloud native supercomputing everywhere, essentially we want to connect HPC at the edge to the main system, right? So we want to create HPC at the edge. We want to bring computational capabilities and different frameworks to the instruments that are running the different kind of experiments and do the first analysis there. And even more than just doing the first analysis there, because if we do bring AI into the edge, we can run the results into an AI framework that they will figure out if the results make sense or do not make sense, and then rerun the experiments again based on those results and so forth. So there will be more HPC at the edge, and then once you get the right results, you want to move them back to the main system that can be part of a different or bigger workload that's running there. So the edge becoming, if you think about it, the edge becoming peripheral of the main data center, and a workload can actually work on the main system and goes all the way to the peripheral, to where the edge is. How you measure something like that, I have no idea. Personally, I have no idea. Probably smarter people that can try to figure out how you can actually benchmark that. And not just, you can benchmark the edge, you can benchmark the main system, you can benchmark the medium in between. How do you do a big one and not just running the full workload? That's a good challenge. That's a good question. Now the converged workloads, it's a big term. Meaning, let's look on Perlmutter just as an example, just because there is a great background there of the system. You can use the system to run AI, right? There's plenty of GPUs there. You can use the system to run the converged workloads, and you can use the system to run, I assume what's called here HPC is the traditional HPC, right? Scientific computing, give or take. Now, what kind of benchmark would I use in order to, list the system somewhere? Do I run Limpak 64-bit, or do I run 32 bits, or run 16 bits, right? It's like depends on what I use in the system. And if I'm doing 16 bits, for example, then Oakridge was already the first exascale system many years ago. So first, I think there are some benchmarks that are becoming less interesting in that part. And then on converged workloads, you can have a converged workload where AI assists scientific computing, but you can have another converged workload where AI create a digital twin of something that you can run scientific computing on it. That's kind of different ways and looks. So definitely benchmarks need to change. In what aspects? I think there is a lot of work to understand the different criteria and how to change those in order to take in order to be able to measure those different kind of scenarios. So it's what I'm saying here. Bottom line is that there is a lot of further understanding and research that needs to be done here in order to figure it out.
Thank you, Jens.
I agree with many of the points that were said previously, and I want to, however, mention that when I look at this question, there's the term edge, and I have sometimes a little bit of a quandary or difficulty of interpreting what edge actually refers to, and the closest definition that I've come across is maybe that edge implies more the inferencing aspects, whereas the central HPC facilities maybe are connected to the training of a model, right? So you more likely have to have these inferencing at the edge, and if that is if that's a notion at least that is that you can agree on, then I think it becomes important to at least find out how we can benchmark inferencing from at the edge, and so there are some libraries that already achieve high performance for inferencing today, like NVIDIA TensorRT, AMD MI-GraphX, and other solutions. So we could simply measure the speed of light of inferencing to come to a kind of more core of capability. But it's of course a larger question that you're asking. But with the converged workloads, one thing I just forgot to add was the precision discussion that we had kind of mentioned peripherally here is also important to inference. So the accuracy versus interplay between accuracy and performance, which is what you, Hayana, mentioned, is a very excuse me, relevant to inferencing too, because there we can potentially reduce our precision and gain huge impact in performance, as also Gilad said with the Gordon Bell in 2018, I believe, on mixed precision AI XFLOP at ORNL. So in that sense, I think here's where we can leverage all the advances in trying to speed up compute to at the edge and measure that. For the converged loads, I agree, it's a more challenging question, because the more components you add to the system, the more challenging it becomes to define what component am I interested in benchmarking. So I think we need to take into account also data transfer metrics. How easily can you exchange training data sets between centers, between the cloud and the center, or in the cloud? They become large. If you think of these billion parameter transformer models that are becoming prevalent, then it certainly is a question, how do you organize the training data for those models? So in that sense, I think converged workflows will have to include data components.
Jens, I just have a question for you. So from your experience in the drug discovery pipeline, where you're mixing HPC, some of the machine learning and AI and so on, what will it matter from the point of view of metrics, basically, to say, I'm achieving good performance or from that perspective, from the application perspective, do you think we need to also move more into a science-driven metrics to also take that into account?
That's an interesting question. I guess we can learn from some of the metrics that have been developed for commercial applications. Thinking in the data space, data has always been more of a topic for industry and for commercial settings, because it just accumulates. And so benchmarks have been developed in the industry to measure data performance, like TPCX and whatnot. These were the ones that we actually at least adapted for scientific use case in the drug discovery pipeline. So I think there's a lot to learn from industry in terms of how to handle large amounts of data, which is something that has been a little bit more niche in HPC centers, apart from of course, having huge file systems, right? But I think there are metrics that we can adopt to science to also measure data access and manipulation performance, ETL performance, these kind of things. And that will be useful to apply to converge workloads, because then we have one more kind of metric that we can apply besides compute.
Thank you, Jens. Heya?
Sure. So I get the coveted last spot, huh, Gilad? Yeah, so I agree a lot with what Prabhat was saying, but I want to kind of give it into a bigger picture, thinking about coupling and where is it running and interfaces and stuff. And what we need to do in benchmarking is really go back to our roots. We need to stop being lazy as application developers and benchmarking our applications and go back to what it looked like in the beginning. So, and in that way, we can move forward. So what I mean is that an application is in itself a workflow, and we need to think of the entire HPC system now as a workflow. So we've gotten lazy because MPI works great, OpenMP works great. We can couple different subroutines, really easily inside of an application. We don't actually think of an application as a workflow anymore because it's so seamless. And really that's what we're trying to get to in this broader space, because now we have more kernels, we have AI kernels, we have data, kernels. And so we need to go back to that language of workflows and think about the task coupling, the data coupling, the data flow, those interfaces. It's almost like, I would say a really good example is CESM, the climate code, right? They have a lot of different components, and then they have the coupler, and we benchmark all the different components and the coupler, and then the total system as well. So that's kind of what I think benchmarking needs to do moving forward, because we have a lot of different kernels that we need to understand their respective performance on different hardware, but we also need to take time to understand the couplings and benchmark the couplings so that we can get to that point where we can predictively understand the performance of the entire ecosystem and stop being lazy about just saying, oh, it's my application. Well, we need to start talking about the components of our application again, different kernels, the communication, data sharing, and really start bringing out that language and, isolating it. Because the thing that I'm seeing in our user community is this might be their workload today, but tomorrow they've decided that their workflow is going to change because they need, there's some new science capability that they want to enable, and the workflow will totally change. And really, in order to remain flexible and give them the best information about how their scientific pipeline is going to work, is to understand how all the components work separately. And then I can make, some sort of projections based on the total workflow. So I think that's kind of what we need to do, is isolate, couple, and so right now I'm in the middle of, thinking about procurement, and it's also how do you deal with, talking with a vendor when you say, I want to benchmark this workflow, and they say, well, I'm only responsible for 25% of it. So that's part of the language of also trying to point the finger of blame, right? That we need to understand, the different isolated components of, what part of our applications or workflows are running, what components they're running on, so that then we can appropriately point the finger of blame at the end and benchmark the system.
Very good. Thank you so much. We are almost at time, but we have a couple more minutes that we can borrow. But I noted that there was a question in chat, so I thought I'll let Jens, if you're online, if you want to ask your question directly, or I can read it for everybody. All right, so he said I should read it. So the question from Jens Stumke, we don't lack benchmarks, but we lack data. If people would collect and share more data from HPC and cloud runtime counters, etc., then we wouldn't need that many benchmarks. Most benchmarks are similar anyways with a few minor changes, but benchmarking is a huge cost, power and labor, and maybe we can offset that cost by preemptive data collection. Too much benchmarking is replicated across people, sites, systems, and sharing would prevent that. Do you agree? And if so, will you contribute your data? And I'll let anyone start since we already went through everybody's order.
I think NERSC is all for sharing data, sharing information. We contribute to benchmarking efforts so that we, don't have to replicate. And I think what would be great is if we can share raw data. So one thing I like to commend, like, Blue Waters, the folks at, NCSA, who shares all their data about how the system works, and they made it available. And I think we're moving in that direction. Hopefully we can do more of that as well for NERSC.
Thanks, Kaya. And Jens made a comment, yeah, he meant raw data to extract information that others may have overlooked.
Yep. I think so. Like tools like LDMS are really important because it's not just the benchmarking itself, but just how the system is operating. So there's a lot of ways to share, to capture raw data. The question is like, well, who's going to store it, and how do we access it? And so maybe the cloud can help us with that. They can take our data, make it easily searchable. But I think we are moving in that direction. The question of logistics is the big problem.
Thank you. Anyone else?
Yeah, I don't think there is a problem sharing data. I don't think there is a problem sharing data. Essentially, some of the benchmarks are there in order to understand the data and to collect specific amount of data. But sharing data, I think you can share data among multiple sites and trying to understand from the data. The question is what data you're looking, right? You can get data of every register that exists in a system, but then what you're going to do with that amount of data, right? You need to put some understanding in the data. And the understanding of the data, those actually, in my eyes, the benchmarks. You set the benchmarks in order to take data and understand something from that, right? To put something that you can understand or learn from the data itself. Now, beyond sharing data, I think there is there is a place for doing something more specific. And I'll give you one example that I mentioned before. Let's say that you want to look into a predictive performance. Right, so predict performance means that you can run the workloads a lot of times and then taking all the information and try to understand, which actually will take a lot of effort. Because you need to run different kind of workloads on the entire system over and over and over and over again. If you would be able to create something simple that can represent a predictive performance numbers, that will be very beneficial because that actually will reduce effort and labor and other things. So I wouldn't throw out benchmarks. Benchmarks are trying to, and you don't need to have duplicate benchmarks, but benchmark trying to make some life easier from effort and time consuming and so forth. But regardless, sharing data, it's always a good thing, as long as you can understand something from the data.
Which is a good point. If we have data, then we can also use it to inform predictive benchmarks, as you say. Because now that we have AI to do scientific and commercial applications, we can also use AI, or at least machine learning, to develop auto-tuning models based on performance models that we have trained on performance data. So in a sense, I think this is beneficial to even executing the actual workloads with the benchmarks in mind to optimize the performance. So thinking about performance and predicting it is definitely healthy for every, or useful for every workload.
So maybe there's a question around, what's the right entity that would run multi-cloud, multi-on-prem HPC benchmarks consistently, and then curate the results and consistently, share it, I guess, with the rest of the community. So certainly, so that might require a little bit of coordination on who really owns that. And I guess it's better if some research entity that's neutral, take the lead on that.
Oh, thank you. We're a little bit over, but we had one last question for everybody. But before we move on to that, I just wanted to mention one thing that could also be useful. Like a lot of the times, the vendors, when they have a new hardware like part or node, they post the numbers, but you'll be like, this is the peak, this is what we got. But like the raw data to actually be able to look at, and when we're running it in the real world, like in real life in the system, we have that node to try to replicate. We don't know how you were able to get that number, so we're trying to back engineer, and having raw data, I think, would be really helpful for our efforts as well.
Yes, and how to curate the data as well to make it anonymous. That's another big aspect of it. There was a lot of data at Oakridge, basically, that we cannot release because it needs to be make it anonymous.
And with the last, maybe in like 1 minute, if each person could take like 1 minute or less. But
yeah,
do you have any?
One more thing, just to add to Jen's. Definitely, you can collect everything from a system, right? Everything from a system, and then create an AI framework and drive everything through that AI framework, and get the insights. All right, this can be a good usage of AI, by the way. But then you will create quote unquote benchmarks, which be what insight you want to see from that data, right? So benchmark will continue to exist in that sense, right? And you need to create those if you do that as insights from data that you collect or something else. That's fine, but it's obviously that's the importance. So I agree with you. It's just benchmarks will become maybe a little bit different, but still those are the insights that we're trying to get.
Thank you. So with the last few minutes, if you have any recommendations, if you don't, it's okay. But what recommendations do you have for benchmark developers in like 1 minute or less per person? I want to start with Gilad, since he loves starting first.
I wanted to be the last one here.
I know.
I'll do it very soon. I think we talk so much about what benchmarks need to be created and what's the missing information and so forth. So there is no reason to say it again. The only thing I would say that for people that actually focus on creating benchmarks and write benchmarks, don't retire. Don't retire. There is a lot of work ahead of us.
Thank you, Jens.
Yeah, I believe that benchmarks need to be actionable, that they actually change the way we run things on the system. So as long as they have that capability, they will be useful. And that means that we can learn on benchmark data and make it available for applying to the code. And then I also think that they need to be comparable. So we need to take into account the heterogeneity in terms of hardware that is ever expanding. And so I don't even know how much time it takes to run this model on that specialized AI chip versus on my GPU. So if I had that information, then it would influence my my workflow decisions. And so in that sense, I think that we need to work on being inclusive also in terms of what we include into the benchmark data.
Great, thank you. Hea?
So I would say think about the goal and that it is not a one size fits all. So the goal of on-prem HPC is different than cloud-based solutions. It's not pure performance. If cloud is looking to create HPC as a service, is that really the same goal as on-prem? So when we start thinking about benchmarks and what we're measuring and the metrics, really do try and think about what is the ultimate goal that we're trying to serve in our different communities, so that we're not trying to create a one-size-fits-all benchmark. We can take similar information, but it does not have to, the final analysis does not have to be the same.
Thank you. And last but not least, Prabhat.
Oh, Gilad, I guess I get to swap things with you. So I guess things are becoming more complex. I think that is a common theme, right? So workloads are becoming converged, AI and HPC. We see these experimental observation data or edge style workflows. So I would say that I think moving benchmarking to address that complexity is really quite important. So, there's a word we like to throw around in Berkeley, I guess, which is holistic. So I would think about benchmarking and evaluating benchmarks holistically. And performance is just one aspect of that. But really, there is also the productivity aspect. And especially when it comes to cloud, people sometimes get worried about cost and so on. So think about benchmark suites that encapsulate all of those dimensions: performance, productivity, and cost. And I think any modern benchmarking tool should span that space and address the complexity in workflows that we see happening, in science for sure.
Excellent. Thank you so much. Any final comments, Oscar, that you want to say? If not.
Well, I think this were excellent contributions by all the panelists. I just want to say thank you, everybody, for agreeing to participate in the panel, and also the audience. And I want to leave that to Verónica.
Yes, thank you very much, all. I think this was an excellent conversation, and I appreciate everybody taking time on their Saturdays to join us. And the recording will be available for viewing later. But thank you again.